So again, thank you very much for the organization. It's a pleasure to be speaking today. I would like to talk about a contractive local adaptive smoothing based on Dörfler marking in a-posteriori-steered pure robust multigrid solvers. This is a joint work with Jan Papes and Martin Voralik, and it can be found in the following preprint. We will be working with algebraic linear systems that come from the discretization by finite element method of polynomial order P for second-order elliptic diffusion problems. And that the approach that we will be taking is a geometric multigrid. The adaptive multigrid in question will rely on two V-cycles. We call the first one a full smoothing, and in here we also construct a localized a posteriori algebraic error estimator. This localization allows us to see where the algebraic error will be largest, and so in the second adaptive local smoothing, we will use local smoothing only in these problematic regions. The way that we mark these regions is thanks to a Dörfler criterion. We can show that each of these two V-cycles contracts the algebraic error P robustly, and that the a posteriori estimators for these V-cycles are P robustly efficient. Then we will give some numerical results. So this is our setting. We have our diffusion problem. Let's say this is our finest mesh. We introduce our finite element space consisting of piecewise polynomials of order P, and this is the problem that we would like to solve. As for our meshes, they need to be shape regular, but other than that, they can be either quasi-uniform or graded, like in this case here. Then we can introduce a sequence of increasing polynomial degrees. And once we have that, we can introduce a sequence of nested finite element spaces. So this gives us a hierarchy of spaces. And what we call a posteriori steering is the approach in which we construct an a posteriori estimator and a solver update through the same procedure, which is a V-cycle with 0 pre-smoothing and a single post-smoothing step. The smoother in question is additive Schwarz or block Jacobi associated to patches of elements. And we also use optimal step sizes in the multigrid error correction stage, and these are level-wise. These are important because they give us a connection between the solver and estimator, which is given here, and eta alg is our estimator, which is localized not only level-wise, but also patch-wise. And it is precisely this localization that, together with a Dörfler type criterion, will allow us to mark the problematic so levels and patches which the estimated error is bigger. Theta is a user-prescribed parameter, and in this case, in this experiment, we also have the exact algebraic error, so we can compare them side by side, and we see that our estimator is actually quite accurate in predicting where the error is going to be. So does this approach pay off? We have here two test cases. We call them skyscraper, and the only difference between them is the jump in the diffusion coefficient, where in the first one it's of magnitude 10 to the power 2, and here 10 to the power 5. And nonetheless, we see that they perform essentially in the same way. So this is an indication that the method is also robust with respect to the jump in the diffusion. And what this graphs give us is that we are essentially marking usually less than 25% of our patches as our problematic regions that need to be smoothed locally. And here we can see the algebraic error decrease. And it is important to notice that we cannot really distinguish the full smoothing steps from the adaptive smoothing steps. So this means that even though in the adaptive smoothing steps, we're only smoothing in roughly 25% of the patches, the quality of error decrease is as if we would smooth globally. So to conclude, we presented a pure robust contractive multigrid solver, which is steered by an a posteriori algebraic error estimator. We've used optimal level-wise step sizes. The adaptivity we use uses local smoothing based on our estimator and the bulk chasing criterion. We can show that the adaptive smoothing substep contracts the algebraic error also pure robustly. And we have given some numerical tests to confirm our results. So thank you very much for your attention.